Right, hi all. Welcome to our first lecture series or lecture content relating to understanding mechanical stress. So these are the things we're going to be talking about. So we're going to be looking at the various modes for component load when it comes to mechanical systems. We're also going to take a look at certain types of mechanical failures. So we're looking at ductile, brittle failure, fatigue, and creep. And we're also going to start looking into what we mean by material stress, what we mean by material. So what constitutes mechanical failure? So mechanical failure could be defined as unacceptable deformation, fracture, relating to engineering components or materials. So in terms of the mechanisms that come together to cause a component to fail, we'll normally start by what's called a crack initiation, which could be attributed to localized microscopic defects within the material, where over time, if there is some element of material degradation and or depending on how a component is loaded, that could initiate cracking within the material. And over time, under dynamic loading, then we can have the crack propagated through the material until eventual failure or damage occurs. So when it comes to mechanical failure, what are the parameters that governs that? So we can look into, number one, the manner to which a component is loaded, the nature of material, whether related to the mechanical and environmental properties of the material. We can also look at the manner and the nature of the environment that the components of the material will be operating in. So we can look at things like thermal conditions, how the level of oxidation that's likely to take place within the material, how the material reacts to a range of media, things like that. We can also look at the state of loading and the rate of loading. So these are some of the factors that can come into play to depict how a component will eventually fail and how long would it take for eventual failure to take place. So here are some classic examples of mechanical systems that have experienced some form of damage. So in this diagram here, we're looking at a wheel for a train, and if you look underneath here, you realize that parts of the wheels are sheared off. So this could be attributed to a number of factors. So you can have what's called corrosion stress. So corrosion stress could be taking place, or stress corrosion, to call it that. So that's a combination of the material being stressed and some element of material degradation due to how the material is reacting with the environment. So you've got that. Okay, you've got some thermal damage here. So this could be attributed to thermal stress in terms of how combustion is taking place within the cylinder. We've also got a failed connecting rod. So this will be a combination of cyclic loading, which eventually cause the connecting rod to fatigue, and eventually fail. We've got more examples here of components failing. So we've got this American football helmet that's cracked. So that could be attributed to impact loads. So at the point of impact, the period of impulse would have amplified the contact force at that point to cause cracking within the component. We've got a mobile phone, we've got the screen cracked, so again that could be attributed to high impact loads. Likewise with this work helmet here. And we've also got this clip, which could be a combination of abuse. So again, the state of the stress on the material or the internal loads that's engaging the component to cause it to fail. Could be one of the factors that's led to the component failing. So this is more. So let's look at what is classified as brittle failure or brittle fracture. So I've classified or characterized brittle fracture as follows. So brittle fracture is characterized by rapid rate of crack propagation throughout the material with minimal energy absorption. So we're more or less looking at the tendency for the material to fail after it transcended its yield point. So if we look at this strain stress diagram here, we're looking at this point here from 2 to 3. So from 1 to 2, this is where the material is behaving elastically. So when we talk about elastic behavior, we're looking at the material's tendency to return back to its original state after the removal of any disturbing forces that's causing the material to deform. Okay? However, when the material exceeds yield point, you realize that the period between 0.2 and 0.3 after the material has undergone what's called strain hardening, okay, to have that additional plastic deformation until it gets to its ultimate tensile point. Once it reaches 3, this is where the material suddenly fails, okay, and this is attributed to the material characteristic that defines the material as being quite brittle. So, as we've more or less inferred in terms of the period between the yield point and the UTS, there's very little deformation in terms of plastic deformation. So in terms of the material's tendency to fail under in terms of brittle fracture, this will increase based on the following factor. So if there is some form of decrease in its operational temperature, then the rate of which brittle fracture will more or less take place will be quite higher. So if you have this situation whereby you've got a material that's quite ductile, and over time, the temperature, or in terms of the environment of operation, drops beyond its glass transition temperature, then you're going to have a situation whereby the material will start to behave similar to materials that are naturally occurring as brittle. So you can actually have that happening. So a drop in temperature could cause brittle failure within a component, and also an increase in the rate of strain. So devoid of whether there is that change in stress or not, if the material is creeping, and we'll talk very briefly about creeping, then the tendency for brittle failure will be more or less evident. So this is why sometimes when you design components and there is a drastic change in temperature, so particularly in environments or communities within the temperate zone, whereby you've designed a component that's supposed to endure conditions during summer, that transition into winter could affect the material's behavioral characteristics in terms of behaving ductilely and then behaving similar to material that's naturally brittle. So these are some of the things that need to be factored in when it comes to material selection. So let's look at the other mode of material failure. So this would be ductile fracture, ductile failure. So unlike brittle failure, whereby there is very little work hardening before eventual failure, when it comes to ductile failure, the material has that capability of absorbing more energy to effect greater plastic deformation within the material until it eventually ruptures. So when it comes to ductile failure, this is quite common in materials that have very good ductile properties, such as metals, so particularly non-ferrous metals or alloys like your aluminiums, your coppers, certain range of steel. So we're looking at structural steel or low carbon steel. So they tend to have these characteristics. So how does the mechanism work? So when the force is applied on the component or material, you have the migration and the nuclearization of the imperfections within the material converging at the highest concentration point to where you've got material voice and things like that. And over time, as these imperfections are convergent, it will get to a point whereby the residual stress concentration within this voice will increase and eventually instigate cracking. So over time, as the force is being applied to the material, you're going to have excessive crack propagation within the material, while the material is also increasing in what's called a lateral strain, and that lateral strain causes necking within the material. So necking is more or less defining a reduction in the sectional profile of a given material or component, and over time it will eventually shear along a plane of 45 degrees as shown in this diagrams here. So that more or less characterizes the failure mode for ductile materials. So we talked about brittle failure and we've talked about ductile failure. So another mode of failure or mechanism of failure is what's termed fatigue. So as the name implies, materials do get tired in their own way. So what characterizes fatigue failure? So fatigue failure is a failure mechanism due to a material being subjected to some form of repeated load or cyclic load, or if you want to classify it as some form of dynamic load or dynamic stress, then that's essentially what that is. So we've got a component here that's been subjected, that's failed via fatigue. And this diagram shows diametrically the mechanism for fatigue failure. So let's assume that you've got a source of fracture. So let's say a scratch on the surface of the component. Over time, as a component is being subjected to some form of dynamic stress, it's going to undergo some measure of ductile failure. And over time, once the component is unable to absorb more energy and undergoing further work hardening and plastic deformation, it will then transition from ductile to brittle failure, where it eventually fails. So that's more or less the basics relating to fatigue failure. And over time, we'll go into this type of failure mechanism in a bit more detail. Fatigue, particularly when it comes to materials that have brittle characteristics, causes most of the failure in mechanical systems. So it is estimated to be around 80 to 85% attribution to components that fail within the mechanical system. So it's very important as designers, as engineers, to really take into account what are the loaded parameters that is likely to affect fatigue failure in components. Right, so another common mode of failure is what's termed as creep. So when it comes to creep, let's assume in this diagram that a component or material is being subjected to a constant load. Over time, the material continues to be subjected to some manner of strain. And the manner of strain is dependent on a number of factors. Number one, it could be how long that particular material is being stressed under a constant load. It could be a combination of how long a component is being stressed by a constant force with respect to changes in temperature. So these are some of the factors that could affect a component to fail under creep. So these are things that need to be adhered to, particularly if a component is being designed to be operated over a longer period of time under constant stress or in environments whereby you have temperatures rising. So these are some of the things that could affect a component to fail under creep. So a classic example would be putting items in a shopping bag. So over time, you realize that despite the fact that you've got this constant mass within the bag, you realize that your plastic bag will start to elongate and stretch, even though you're not adding more content in the bag. That is a simple description of what creep is. Okay, so I've defined creep as follows. So creep is also termed cold flow. So this is a failure mechanism, as I stated. It could be desired, it could be not desired. But if it's not desired, then that will constitute creep as being a failure mechanism, where the material experiences deformation due to a time-dependent strain. Okay, so we've got constant stress in the material. However, over time, the material is deforming. Okay. So as I've more or less pointed out, when it comes to creep, the following factors can influence the rate of creep. So again, we've got time. So how long is that force being applied on the material? So this is where the period of stress becomes a factor. Changes in the environment and the professional parameters. So if the environment around the material is changing due to increase in the temperature differential, then that could instigate or influence how quickly a material is strained. And you've also got the material's property too. So dependent on what the mechanical and environmental properties of the material is likely to be, then these elements need to be factored in to safeguard the material's tendency not to creep over time. So this is a very basic introduction into creep, and hopefully over time we'll go in depth into creep failure.